Hello students, welcome to Adantal. Good evening to all.
Good evening, sir. Good evening, sir.
Good evening Soham.
Good evening, sir.
Good evening Smutishri. Good evening everyone.
Good morning, sir.
It's good evening, not good morning. Okay, so today we will discuss about Miller indices and the rest of the topics from crystal structure. But first of all, let us try to understand what Miller indices are. Good evening, Divya.
Good evening, sir.
Miller indices. Now, actually, what we do is we consider that crystal lattice, it is composed up of parallel planes, parallel infinite planes. Okay, why we consider so, or why we assume so? Because that way we are easily able to understand the X-ray diffraction phenomena. If we consider that the crystal it is composed up of various parallel planes, and then the Miller devised a method to calculate the index corresponding to those parallel planes. That how we can identify those planes, and those index they are called Miller indices. Okay, a crystal lattice may be considered as an aggregate of a set of parallel, equally, good evening Durga, equally spaced planes. Of course, the planes they are passing through the lattice points. Through the lattice points. And these planes they are called lattice planes. And the perpendicular distance between adjacent planes it is called interplanar spacing. No, they cannot be, because they may be composed of the different set of lattice points. But all the parallel planes, definitely they will be of same size. If you consider one set of parallel planes, then they are, of course, a given space lattice may have an infinite sets of lattice planes, and of course each set of planes they will be having different interplanar distance between them, and that is called characteristic interplanar spacing. Characteristics means this is the unique property of those planes. Okay. Yes. Yeah, Prachi, I'm coming to your question. See, Kanaya, first of all, space lattice means those Bravais lattices that we have discussed. We have discussed the Bravais lattice types in 2D and 3D. Cubic, tetragonal, rhombohedral. Do you remember?
Yes, sir.
Those are called space lattice. Okay. Now, about the definition of Miller indices. Now, Prachi asked me. Okay. Now, see. You remember, Prachi, we did one article on rotational symmetry. So yeah. I made one diagram in that particular article like this. These are the planes. This is one plane. This is another plane, and then there will be another one. So these are parallel planes. Na? So they will be having particular distance between them. Okay. So how to identify these planes? Or for example, you can make these planes also. Na? Let me tell you in much better way. These are also the planes. These are also the planes. Na?
Yes, sir.
Now, how to identify that we are talking about which set of planes, whether this one or this one? For that, Miller devised the method to calculate the Miller indices, and they will be unique for a set of parallel planes. Means Miller indices they're going to be different for these black planes and for these blue planes, and similarly all set of parallel planes. Now here.
Yes, sir.
So means these are some set of parameters which we use to identify the set of parallel planes. Not a single plane, but all set of parallel planes. They are represented by the same Miller indices. HKL.
Sir, what is HKL?
Miller indices, na? These are the representations for Miller indices. Name by default. Of course, we cannot change their name. It's not like that that I can name them as ABC or DEF. I cannot do so because by default they are written as HKL. And they will be having integer values. These HKL, they will be having integer values, or they may be negative also, but they cannot be in fraction. Okay, definition clear?
Yes, sir.
So
Yes,
right now I have discussed only definition, but rest of the things I will be telling you. Now, you need to remember these important points. You can write the heading that important points to remember regarding Miller indices. All the, as discussed earlier also, all the parallel equidistant planes have the same Miller indices. A plane parallel to, so these are the short tips, okay, parallel to one of the coordinate axis. So if I draw a plane parallel to one of the coordinate axis, so when I'm saying that it is parallel to suppose z axis, then according to you, where it will intersect the z axis? Can you tell me? If it is parallel to z axis, it means it will never intersect z axis, or we can say it will intersect z axis at infinity. Okay. And when it intersects z axis at infinity, then it means the z intercept will be infinity. Clear?
Yes, sir.
Yes, sir.
If the Miller indices, now if there are two planes whose Miller indices are in the same ratio, for example, one set of planes it is having Miller indices 844 and the other one they are having 422, or for example 211. Now these three sets, they are in same ratio. Na?
Yes, sir.
The second one is half of the first one and the third one is 1/4. It means all these planes, they are parallel to each other. All these planes are parallel to each other. And last, if HKL are the Miller indices of a plane, then the plane cuts the axis into H, K, and L equal segments, respectively. So this is the summary of the points that we need to remember regarding the Miller indices. So now we will calculate the Miller indices of some of the planes, and of course some problems related to them. So then you will be able to better understand this topic. Okay. Arun, HKL means, suppose H is 4. It means that particular plane, those set of planes, it is cutting the x-axis into 4 equal segments. If H is 4 means 4 segment, K is 2 segment, L is 2 segments, like that. Equal segment means they will be in the ratio of their primitive translational vectors. That is ABC. If ABC are the primitive translational vectors, so in terms of them. Okay. So it will be clear with the help of the numerical. See, obtain the Miller indices of a plane which intercepts A, B by 2, 3C. Now see, these are the intercepts. If B by 2 is the intercept, it means it is cutting the y-axis in 2 equal segments. Huh? Okay, here it is one segment, like this. But it will be in the ratio. If I'm considering this as 2, then this will be 1. But then this will become 1 by 3. But as they cannot be in fraction, so we need to multiply them by some number. Now listen to me carefully. What has to be done in order to calculate the Miller indices? So what we have to do is, the very first thing is we have to divide these. You can say these are the intercepts. So we have to divide primitive translational vectors by these intercepts. That is the method. Now what are the primitive translation vectors? They are ABC. Na? Of course they are given. Okay. So first divide all the unit cell dimensions, you can say. Unit cell dimensions or primitive translational vectors by the respective intercepts. So is it clear? This is the shortcut one. Of course, in some of the books, you will find that they are saying you have to divide the intercept by the respective primitive translational vectors and then you have to get the reciprocal. But this is the shortcut one. Now, what are the unit cell dimensions or the primitive translational vector along x-axis? It is A. So I have to divide A by A, B by B by 2, and C by 3C. So then it becomes 1, 2, 1 by 3. Please check. Is it clear up to this point?
Yes, sir.
Everyone?
Yes, sir.
Now,
Yes, sir.
now we have discussed that these Miller indices, they have to be integers only. Miller indices can be integers only. Na? So what has to be done in order to convert them into integers? What should we do?
We can multiply by 3. Multiply with 3.
So multiply throughout by 3 to convert these into integers. So it becomes 3, 6, 1. So these are the Miller indices. Now, anyone having any doubt regarding the calculation of Miller indices or what Miller indices are? Please tell.
Sir, A vector, B vector, and C vector, these are like in any directions, or they are along the coordinate axis that we consider?
They will be along the mutually perpendicular axis, no? X, Y, Z.
Okay.
I'm saying X, Y, Z, so these are perpendicular. They cannot be in any random direction. No, it has nothing to do with linear algebra. We are just dividing the lengths of those primitive vectors. We have taken their magnitude only. No? It has nothing to do with vectors or the linear algebra. It is just simple division and multiplication. That's it. These are the magnitudes of those A vector, B vector, C vector. And intercepts, they are also given in the terms of ABC. Clear?
Yes, sir.
No. Another one. Find the Miller indices of a set of parallel planes. Which makes intercepts A, B, and C being primitive vectors of the lattice. So what has to be done in this case? So intercepts are 3A, 4B. So what about the intercept on Z axis?
Infinity.
How you get?
It is parallel to Z axis, no?
Yeah. And parallel to Z axis, the intercept Z will be infinity. So it means intercepts, they are x equal to 3A, y equal to 4B, Z equal to infinity. Now, what I have to do is actually A by X, B by Y, C by Z. Now put their values. So it will be 1 by 3, 1 by 4, 1 by infinity, and 1 by infinity is nothing but 0. Na? So now in order to convert them into integers, what I have to do is I have to multiply by 12. Na? So this will become 4, 3, 0. So HKL is 4, 3, 0. Please check. Clear?
Yes, sir.
Noted everyone?
Yes, sir.
Now let us see who is able to solve this one then. In a crystal whose primitives are 0.12, 0.18, and 0.2, a plane 2, 3, 1 cuts an intercept along the x-axis. Find the length of the intercept. Means x is given to you. Find the length of the intercepts along the y and z axis. Means you have to calculate y and z. So A, B, C are given to you. This is A, this is B, this is C, this is X. So you have to calculate y and z. Na? So how we can do that? Please, anyone? Yes. What was the form of H here?
HKL is already given to us. 2, 3, 1.
Of course, they are given. But how they are related to A and X? AX.
X, Y, A, Y, Y.
Now come here on the previous slide. So what we have done actually, in order to calculate H, now see here, in order to calculate H, first we have done A by X, and then we have multiplied by some number. Na? So if I call that number as N, then this H is of the form N A by X. This is of the form N B by Y. This is of the form N C by Z. Na? Isn't it? Because we are multiplying A by X, B by Y, C by Z by some number, some common number, some common integer. So if we call that integer, then HKL, they will be of this form. Na? Clear? Is it clear?
Yes, sir.
So now we can make use of this condition that H is NA by X and K is NB by Y and L is NC by Z. Now, because we know H, A, X, B, K, so if we divide H by K, what do we get? It will be A, Y by BX. Na? And from here, can we get Y? Please check. Because that N is unknown to us na, in this scenario. Clear or not? Because we are unaware about the other intercepts. So N is not known to us. So we need to eliminate that N. So that's what I have done by dividing them. So now I can substitute the values of H, B, and of course X, K, A. So these two, they will get cancelled. So 0.12. Na? So I'm able to calculate y. So in the same way, you can calculate z either by dividing h by l or k by l. So it is up to you. So if you are doing h by l, then you will be getting az by cx. Then this will give you z hcx by la. So 2, 0.2, 0.12, L is 1, A is 0.12. So it will be 0.4. Na? Please check it out. So very easily we are able to get this. Clear?
Yes, sir.
Now suppose two planes are given with their Miller indices, then how to get the angle between two planes? Now, suppose Miller indices, you can write if instead of suppose, if Miller indices of two planes are H1, K1, L1 and H2, K2, L2, then the angle between the planes is given by, so cos theta, then the angle theta between, that will be more appropriate. So then I need not tell you that theta is the angle between the planes. So this is the formula then. Just like the dot product of vectors. So means we are treating these HKL as vectors. So we have taken A dot B in the numerator, and then in the denominator it will be A mod into B mod. And this is there in cubic system. And of course there are different formulae for different systems, but cubic one is there in your syllabi. Okay? Clear? Is it clear?
Yes, sir. Yes, sir.
Now let us calculate the angle between some planes. Okay? So with the help of this formula, now you will tell me. Calculate the angle between 1, 1, 1 and 0, 0, 1 direction in a cubic crystal. So it will be 1 into 0, 1 into 0, 1 into 1. We are not calculating the angle from geometry CL. We are just calculating it from simple formula by using the vectors formula, dot product of vectors. We are not calculating it geometrically. So theta is cos inverse 1 by root 3. And of course, you can calculate this angle with the help of your tables, etc. And this will turn out to be around 54.75 degrees. Please check. Clear?
Yes, sir.
Another one. Calculate the angle between 1, 1, 1 and 1 bar, 1 direction in a cubic crystal. Now, what do we mean by this 1 bar? Actually, this 1 bar means minus 1. So whenever there is a bar over Miller index, it means it is a negative of that. Means 1 bar means it is minus 1. It is minus 1 like that. Okay, so you have to consider them as minus 1. So I will also make some of the planes. Then you will get to know. So 1 bar means minus 1. Okay. So again, formula. Please keep yourself muted. This, then 1 square, 1 square, 1 square, minus 1 square, minus 1 square, 1 square. So this will become minus 1 plus 1, root 3, root 3. So minus 1 by 3. So theta is cos inverse minus 1 by 3. How much? Is it 109.5 degrees?
Yes, sir.
Please check everyone. So now can you calculate the angle between any directions in a cubic crystal? Please tell.
Yes, sir.
Yeah, na?
Yes, sir.
Yes, sir.
Okay. There is one question with me for you regarding the Miller indices. There's that question. Yes. This one we have also done. This one type. This is somewhat different from the earlier ones. A certain orthorhombic crystal has a ratio A is to B is to C of 0.429 is to 1 is to 0.377. So there are three set of planes. This you have to do. So what about the first one? These are ABC and these are XYZ intercepts. So what we have to do? We have to divide ABC by XYZ. So for the first case, it will be this, isn't it? Clear?
Yes, sir.
So this is approximately 2, this is 1, and what is this one again? 2, no, I think. So Miller indices are 2, 1, 2. Please check. For first one, 2, 1, 2. Clear?
Yes, sir.
What about second one? 1:1. 0.377 by 0.754. This is half now. This is also half. It means we need to multiply by 2 now. So it is 1, 2, 1. Okay. Let us call this as second part. This is first so that we are able to identify. And now third one. 0.429 by 0.429. 1 by infinity and then 0.377 by 0.126. So this is 1, this is 0, and this is 3 times. So 103 clearly. Please check.
Yes, sir.
Clear to all?
Yes, sir.
Yes, sir.
Distance between parallel planes. How to get the distance between these parallel planes whose Miller indices are known. So we have discussed now that Miller indices, they represent an infinite set of parallel planes. So means they will be having some distance between them. So what is that distance? How that can be calculated with the help of those Miller indices? So as we have also asserted earlier that this distance is going to be unique for different set of parallel planes. Means it should depend upon their Miller indices. Only then it will be characteristic of the particular set of parallel planes. So then this formula for the cubic case, first of all, for cubic one, this formula is BHKL. It is A by x square plus k square plus l square square root. Because in cubic, A equal to B equal to C now. Cubic, cube. Okay? Clear?
Yes, sir.
And let me tell you the formula for other systems also. For tetragonal, the formula is actually 1 by DHKL square, x square plus k square by L square, by A square, sorry, L square by C square. You need to remember these formulae. Of course, they are going to ask you about cubic only, but I have also given other formulae. And you can see they depend upon ABC or HKL. So these are the formulae for various systems. So only these many you need to remember. Okay? Clear?
Yes, sir.
Yes, sir.
Now let us represent some of the parallel planes. Okay? Let us represent. Suppose this is x-axis, this is y-axis, this is z-axis. And similarly in this case also. Then how I can represent 1, 0, 0 plane? Then this will be, this front face, it will be 1, 0, 0 that I'm shading. Okay, so that is the origin, that far corner. Then this plane is 1, 0, 0 that I have represented. Can I write 1, 0, 0 over here? Please check. Okay, clear? And this plane, what about this plane?
001.
Very good. This is 0, 0, 1. Because this is parallel to xy and cutting z-axis now. And what about this one then? Let me use the different color. This one. Now this is cutting y-axis. 0, 1, 0. Very good. Either you can put commas or you can remove these because they are not required. These are HKL. Now let us see some other planes. Now what about 1, 1, 1? 1, 1, 0 first of all. 1, 1, 0. X, Y, Z. Now 1, 1, 0 means it is cutting x and y axis and parallel to Z. So 1, 1, 0 is this plane. Now please see. This blue one, okay? This plane. Is it clear? 1, 1, 0 plane. 1, 1, 0 means which is cutting x and y axis at some point, but which is parallel to Z. Now what about 1, 1, 1? Cutting all the axis. This plane. This is 1, 1, 1. Again, I have put commas. Sorry. Please check. Are they clear?
Yes, sir. Yes, sir.
Please check everyone. Now, what about 1 bar 0, 0? What about 1 bar 0, 0? Now, suppose this is the origin. This is z-axis, this is y-axis, and of course here it is x-axis. 1 bar 0 0 means which is cutting x-axis at -1. So this back plane, because now I have shifted the origin. This is 1 bar 0 0. Please check. Is it clear or not?
Yes, sir.
Because now at that phase x will be -1. Na? Clear to all?
Yes, sir.
Now what about 1 0 1?
Parallel to y-axis and cutting both x and z-axis.
How to make this?
It would be the side of the cube.
Suppose this is z, this is x, this is y.
So the back face of the cube. But the origin is here at the
If it is parallel to y and it is cutting z and x, then it will be like this according to me. Just to make you visualize better, I have shifted x and y. There is nothing special about this. This way it will be clearly visible actually. This plane. This is not cutting y axis, you can see. It is only cutting x and z. Clear? This is 1 0 1. Okay. What about 0 1 1? Again taking the same axis, z x y. So 0 1 means not cutting the x axis, but cutting y and z axis. So 0 1 1 will be like this then. This plane. The diagonal one, the body diagonal. This is 0 1 1. I think now they are clear. Okay. Any doubt regarding these planes?
Sir, can you please repeat the last one?
0 1 1.
Yes, sir.
So
Just so I can visualize this.
0 1 1 means which is not cutting the x-axis but cutting the y and z axis. So you can see this plane, it is parallel to this line. Na? It is not cutting the z axis. It is only cutting this line. This is y axis, and it is also cutting this line, top one. It is cutting the z axis over here, and it is cutting the z axis over here. It is not cutting the x axis. You can see the difference between this plane and this plane. You will get to know. That plane was cutting x and z and was parallel to y, but this plane it is parallel to x. If it would have been cutting x axis, then this would have been like this. Something. Okay. The line would have been like this. These lines are cutting x axis, and these lines they are parallel to x axis. Please check.
Yes, sir.
So means it is not cutting x axis, but these lines they are cutting. You can see this will cut y axis. This will also cut z axis at some point.
Yes, sir.
Now let us calculate the planar density of various planes in simple cubic, body centered cubic, and face centered cubic crystal. Planar density means number of atoms per unit area in particular plane. Okay, so you can give the heading different planes in simple cubic structure and their density. Of course, when we are saying that they are plane, so plane means planar density. It is not the normal density, that is mass over volume, because we are talking about the 2D structure. Plane is a 2D structure. It is not a 3D structure. Here. Now, first one, we are talking about first of all 1 0 0 plane. Now 1 0 0 means it is covering your 0 1 0 0 0 1 also. Okay, because it is cubic, so all will be equivalent. 1 0 0 0 1 0 0 0 1. Now, in this case, let me show you. Actually, what I'm trying to do is, in the 3D case, we represented atom by spheres, but because it is 2D, so here the atoms they will be circles like this, the dotted one. But only 1/4 part of that circle it is present within this particular plane. This is x-axis. So here I have made this 1 0 0 plane actually. First of all, this is 1 0 0 plane. And in simple cubic structure, because atoms they are present at corners only, so here 4 circles they will be present at these 4 corners, and that is how this plane will look like along with the atoms. So there will be another atom like this. If you complete this one, you will get to know that this one will be touching this one, and so on. Is it clear? Or should I make the complete diagram, all the 4 atoms? Clear or not? Let me make it.
Yes, sir.
Clear, sir. Clear.
So it will be like this. Okay. And again, this edge length will be equal to 2r. Same thing. The only thing is now we are representing the atom by circles instead of spheres. That's it. Okay. Now, how many atoms are there in this particular plane according to you?
1.
How?
The quarter of each circle is coming up now, so it will make up 1.
It is 4 times 1/4, that is 1. And how it is quarter? Because the angle is 90 degrees. So I told you earlier also that how to get the fraction. Total angle is 360 degrees and here it is 90. So 1/4 fraction of the atom is there, and there are 4 of them. So only 1 atom is present in this particular plane. Now what is the area of this plane? It is a square, because we are talking about the cube. It is a square and side is a. So area will be 1/a square. Okay. So number of atoms per unit area or planar density You can also call this as planar density, number of atoms per unit area. This will be 1 by a square. Is it clear?
Yes, sir.
Now, what about packing fraction according to you? Packing fraction. Now, how many atoms were there? Only one. Na? So here it will be defined as area occupied by atoms, n effective into area occupied by atom by area of plane. Instead of unit cell, now we are having plane. Na? So here atom is only one, and we are representing them by circles of radius r. And what is this A? It is 2r, 2r. Na? And what is this value? Can anyone get me this value? Pi by 4.
Sir, 90?
How much?
95 or 45?
You are not calculating the angle.
0.78.
You have to put the value of pi.
0.75.
0.785. Okay. So it means 78.5% space is occupied. Okay. Clear to all?
Yes, sir.
Yes, sir.
And same is the thing about 010 and 001 planes. Now, let us do the same thing regarding 110 plane. 110. And same will be the case for 101 and 011. Okay. First of all, let us draw 110 plane. This is 110 plane. Now, atoms are present at the corners only. So along the same edge, they will be touching each other like this. But because this is the phase diagonal, so atom will not be touching each other along the phase diagonal. So the structure will appear to be like this one. Please check everyone. Is it okay? This is A, this is root 2A. Na? And A is 2R, so that is more than 2R. Na? So atoms, they cannot touch each other along the phase diagonal. Now, how many atoms are there? How many atoms?
1.
Yes, again 1 4 into 1 by 4. Because again 1/4 fraction is there. And area of plane.
Is A into root 2A.
Yes, because it is a rectangle. So it will be root 2A square. And a number of atoms per unit area means planar density. What about packing fraction? Only one atom is there. So it will occupy an area of pi r square. And A is 2R, so it will be pi r square by 4 root 2r square. So pi by 4 root 2, how much? Of course, this will be less than the earlier value. What is the value you are getting?
0.555.
So 55.5%. Of course, we can see that a lot of space is empty as compared to the earlier one. Because here also, because the area is greater, but we still have 4 atoms. Area is greater as compared to 100. So obviously the packing fraction, it is less. Clear?
Yes, sir.
No. 111. This one. This is 111. Now atoms, because all these are phase diagonals, so atoms, they won't be touching each other. So they will be having some gap between them like this. Okay. Now, what kind of triangle is this?
An equilateral triangle with 60 degree.
60 degree. So 1/6 portion is there of each atom.
Yes, sir.
And there are 3 of them.
So 1/3 of the circle is
One third, half.
yeah, half of the
So it is 50 by 360, 1 by 60. And then it has to be multiplied by 3. And what is the area? How to calculate the area of the plane?
half by root 3 by 4 A square.
And side is root 2A. Na? So this comes out to be, you can say root 3 by 2A square. Please check everyone. Number of atoms per unit area. Half by root 3 by 2A square. So 1 by root 3A square. So packing fraction, how to get the packing fraction? It will be half into pi r square because half atom is there. And then root 3 by 2 2r square. Half pi r square by root 3 by 2 into 4r square. R square will get cancelled. So pi by 4 root 3, na? How much? Point 453, is it?
Yes, sir.
So further less, because this is having even more area and the atom is only half, whereas this was 1 in case of 110. No, area is not greater, but atom is only half. Actually, per atom it is greater. Actually, in totality it is not greater because that was root 2A square, and this is less than that. Clear?
Yes, sir.
Yes, sir.
So now we have to do the same thing in FCC and BCC, and they are going to be much easier for you now because we have already calculated the area of all these planes, and we will be considering the same planes. So means half of the things they are already known to you. So different planes in FCC structure and their density. Again, first one, it will be 1, 0, 0. Now, what will be the difference from the earlier case? Anyone? There will be an atom within the phase center, like this. The picture will be like this, na? Because now the atoms, they do not touch each other na, along the same edge. Edge length is greater than 2r in case of SEC. Please speak up.
Yes, sir.
Yes, sir.
Total atoms will be 2.
Yes. Because there is one more at the phase center na, as compared to simple cubic case. Clear?
Yes,
Of course, the diagram is not symmetrical as far as I am concerned. Those curves, they are a little bigger. Na? Now I think it will be more symmetrical. Now, number of atoms. It will be 1 plus 4 into 1 by 4. 2, na? And we have already calculated the area of plane. What was the area A square? Because it is a square na, with side A. So number of atoms per unit area. 2 by A square. What about packing fraction? Let us see who is able to calculate the packing fraction. Anyone? Now there are 2 atoms, na? So area occupied by the atoms will be, and area of the plane is A, and in FCC A is 2 root 2r. Na?
Yes, sir.
Again pi by 4. Na?
Yes, sir.
Similar to that simple cubic, I think. Na? We also get the same value. Na? What was this value? 0.785. Na?
Yes, sir.
So please check everyone. So it's clear to everyone na, that how to calculate the atoms, area, packing fraction and all. Just similar to the 3D case. There we have been calculating the volume and here we are calculating the area. That's it. Clear?
Yes, sir.
Now 1, 1, 0. Z, X, Y. Now, one atom will be there at the phase center and half of this will be present like this. Please see. Please check. Is it clear? There is an atom at the phase center. Na? So one full atom will be there. And half of that will be present inside this particular 1, 1, 0 plane. Na?
Yes, sir.
Because half will be outside this. So that's what I'm representing by semicircles. Now how many atoms are there? 4 into 1 by 4 and 2 into half, na? Because they are semicircles. So 2 atoms are there. And what was the area of plane? Root 2a square. We have already calculated the area in simple cubic case. A root 2a. So number of atoms per unit area. So 2 by root 2a square means root 2 by a square. So what about packing fraction? So 2 atoms are there. 2 into pi r square and root 2a. A is 2 root 2r. So it will be like 2 pi r square root 2 into 8 r square. So it will be pi by 4 root 2. Na? How much? This one also we have calculated, I think, 0.555. Na?
Yes, sir.
Clear? Yes, beta. Done, everyone?
Yes, sir.
Now what about 1, 1, 1 then? No. The scenario will be like this. There will be semicircles. Like this, no? Please check. Because all these are phase diagonals. Because of the atoms present at the phase centers, half circles will be there. Is it clear or not?
Yes, it's clear.
So area we have already calculated. Now what about the number of atoms? So these were 3,
Sir, 2.
3 into 1 by 2. So it is half plus 3 by 2, which is equal to 2. And the area of plane was root 3 by 2a square. This we have already calculated. It was root 3 by 4 side square and it came out to be root 3 by 2a square. Na? So number of atoms per unit area. Number of atoms per unit area.
4 by root 3a square.
Yes. You can in fact calculate this if you know about A for a particular structure. Na? If you are given A in the exam, then they can ask you about the mathematical value also. Per millimeter square, per centimeter square, it's like that. Because A is generally in angstrom. Na? So packing fraction. So 2 atoms are there. 2 into pi r square. Actually, I'm calculating the packing fraction from this first one only. Because from this one only it is clear that there are 2 atoms. Okay. From this one it is not clear. Na? So I'm using only this expression. Because there are 2 atoms and then I'm also substituting for A. Clear? Root 3 by 2 and it is 8 r square. So r square will get cancelled. Pi by 2 root 3. Na? So this will be double of that 0.455 value. So 0.91 around.
0.90.
0.90.
90.
906.
Yes, sir. Clear.
Done everyone?
Yes, sir.
Now same thing in BCC. So different planes in BCC structure and their density. Again 100 plane. Now you will tell me what is this density and all. Number of atoms, area of plane, everything you have to tell me now. Number of atoms per unit area. Now how many atoms are there? It will be just like simple cubic, na?
Yes, sir.
Like this, na? This is A. This is also A. So again, it is 4 into 1 by 4. 1. What is the area of plane? Again, A square. 1 by A square. So packing fraction will also be similar to that simple cubic one,
5 by 4.
isn't it? But no, but A value is different. Na? Sorry. A is 4r by root 3 in this case, na? So it is going to be different. 16 by 3 r square. Na? So r square will get cancelled. It is 3 pi by 16. Please get me this value. Okay, 0.589. Na? Just because that A value is different, so this is coming out to be different. Otherwise, the rest of everything is same, na? Just like simple cubic. Clear?
Yes, sir.
Yes, sir.
So 110. This solid state physics part, this is also very scoring. And this is interesting also. Okay, straightforward questions they are asked from this topic. And also the syllabus is less, na? So it can enhance your chances of clearing IIT JAM. So do this part carefully and wholeheartedly. Now what about 110?
Total number of atoms will be 2.
Yes, the one which is present at the body center, it will contribute a full circle, na?
Yes, sir.
Like this. But of course, it will be touching these atoms, na? So it is very tedious task to make a diagram in the actual sense. So that particular atom, it will be touching all these actually. Is it okay? Like this. Clear?
Yes, sir.
So number of atoms, area of plane, number of atoms per unit area. Number of atoms will be 2, na?
Area of the plane would be A into root 2A.
Yes, again similar.
Number of atoms per unit area is 2 divided by root 2A square.
So what about packing fraction?
2 into pi.
2 atoms are there. A is 4r by root 3. Na?
Yes, sir.
So 2 pi r square. Root 2 into 16 by 3 r square. R square will get cancelled. And then it will be like 3 pi by 8 root 3, isn't it? 8 root 2, sorry. How much? What is this value? 0.833. Please note down. Huh? Then last 111. Of course, we have made it so many times now. So only those 3, na? Because the body centered one, it is not going to contribute. Only these 3, just similar to the simple cubic one. So how many atoms? Half.
1 by 2.
So area of plane,
Root 3A square.
root 3 by 2A square. Because this was root 2A, root 2A, root 2A. And the number of atoms per unit area.
1
1 by root 3 square.
A square.
So in the packing fraction. it will be half atom. So half into pi r square. By root 3 by 2, 4r by root 3 square. So pi by 2 r square. 16 by 3 r square. No? So how much? This 2 and 2 will get cancelled, r square will also get cancelled. So it will be like root 3 pi by 16. No? Please check. What is the value?
0.34.
So clear to everyone how to get the planar density or the packing fraction, number of atoms, etc.
Yes, sir.
Yes, sir.
So we will end up our discussion here, and tomorrow I will discuss you about the HCP crystal and then graphene structure also. So these two structures are left, and of course tetrahedral and octahedral voids, and then questions related to this crystal structure. Okay, okay, beta. Bye bye. Take care.
Bye, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir. Thank you.
Sir.